Section: Introduction. In this section, we explore how second-order optimizers can enhance the efficiency of language model pre-training compared to AdamW. These optimizers can provide better generalization from the same training data by leveraging statistical relationships between model parameters. However, they often come with higher computational costs, and researchers typically use wall clock time and flop counts to simplify the complexity of these algorithms. Yet, these metrics do not fully capture the essential trade-off between computational and time resources, which is crucial for large-scale pre-training. We note that Adam and AdamW have been the leading optimizers for neural networks due to their data efficiency and minimal increase in computational cost. Second-order optimizers have the potential to challenge this dominance by offering similar or better data efficiency without losing computational advantages. However, relying solely on time or flop counts does not adequately demonstrate their superiority over AdamW. Pre-training tasks vary widely in model architecture, data size, and available resources. To truly understand an optimizer's practicality, we must consider the trade-off between compute and time resources, particularly how we can reduce training time by using more devices. A significant factor in this trade-off is batch size. Increasing it can speed up data processing but may reduce data efficiency. A good optimizer should support larger batch sizes for faster training while maintaining data efficiency and computational effectiveness. We aim to illustrate how a second-order optimizer can provide a better compute time trade-off compared to AdamW by plotting the compute and time resources needed to reach the same target loss with different optimizers. This allows us to compare them effectively. We focus on Muon, a straightforward second-order optimizer, and build on recent findings that show it is more flop efficient than AdamW. We assert that Muon enhances the compute time trade-off with variable batch sizes, giving practitioners more flexibility in resource allocation. We also analyze Muon's data efficiency compared to AdamW in scenarios with large batch sizes. In the latter part of our paper, we tackle the challenge of selecting optimal hyperparameters for pre-training. We introduce the maximal update parameterization, MUP, which helps transfer hyperparameters from smaller to larger models, easing the hyperparameter search process. We demonstrate that MUP works well with Muon, extending previous results seen with AdamW. While MUP is theoretically sound, it can face practical challenges, requiring adjustments across different model sizes. We propose a simple, telescoping algorithm for training a final model that accounts for estimation errors and adjusts the search grid across model scales with a modest additional computational cost. Our paper serves as a practical guide for optimization in pre-training, recommending Muon over AdamW for its flexibility and data efficiency with large batch sizes, and suggesting the use of MUP for efficient hyperparameter searches at scale. We support our conclusions with extensive experiments, varying model sizes up to 4 billion parameters and batch sizes up to 16 million tokens, while examining the effects of data distribution and architecture. Section Summary. In this section, we explore the advantages of second-order optimizers like Muon over AdamW for language model pre-training, highlighting their potential for improved data efficiency and flexibility in resource allocation without compromising computational efficiency. We also discuss the importance of understanding the compute time trade-off and present a method for optimizing hyperparameters using the maximal update parameterization, MUP, to enhance training effectiveness across varying model sizes. Section: Muon improves the compute time trade-off. In this section, we discuss how Muon enhances the balance between compute time and performance. We begin by reviewing Muon, which is a transformer language model that relies on matrix weights to define its feed-forward and attention layers. We assume a standard approach where a weight update is based on a transformation of the gradient from a specific batch. Muon operates like a matrix-based steepest descent method with a focus on regularization, and it optimally finds solutions without directly computing singular value decompositions by using Newton-Schultz iterations. In practice, we combine Muon with techniques like Nesterov momentum, scaling the learning rate, and weight decay, maintaining only the first moment initialized to 0. During updates, we calculate the gradient while considering momentum and weight decay parameters. We also use a constant to normalize Muon updates, ensuring they align with the AdamW updates, which is beneficial since AdamW is used for updating embedding and normalization parameters. We provide well-tuned hyperparameters for Newton-Schultz that effectively manage singular values. We focus on Muon for several reasons. It has a straightforward derivation and implementation, allowing us to highlight the practical advantages of second-order methods. We can simplify more complex algorithms like shampoo and soap to Muon, making it a fundamental optimizer in this category. Additionally, Muon has a minimal memory requirement compared to other optimizers, which is advantageous for distributed training. The computational overhead of Muon compared to AdamW decreases with larger batch sizes, making it suitable for large batch training. Finally, Muon requires minimal tuning, primarily for the maximum learning rate and weight decay, which are compatible with AdamW, facilitating easy comparisons. For our architecture, we utilize a modern decoder-only transformer model based on Gemma 3, which improves attention stability. We simplify our approach by using only global attention layers and compare our results with Gemma 2 in our studies. Regarding data distributions, we use a diverse mix of pre-training data from various sources, including GitHub code, math blogs, books, and web content. We focus on text and code, using high-quality web text and filtered Python code. We chunk our input sequences to a length of 8,192 using a specific tokenizer. To ensure effective training, we aim to meet or exceed the optimal token budget, training different model sizes on corresponding token amounts. We implement AdamW from the Optax library and use our in-house JAX implementation of Muon for all layers except for embedding and normalization, where we apply Optax Adam. We conduct our training on TPU v5P chips, achieving significant model utilization. For hyperparameter tuning, we perform a detailed sweep at the 100M model scale and validate our choices at the 500M scale. We also explore different batch sizes for the 1B model and apply those insights to the 2B and 4B experiments. Throughout, we follow a learning rate schedule that includes a linear warm-up and cosine decay. Section Summary. In this section, we review Muon, a second-order optimizer that simplifies the implementation of steepest descent with spectral norm regularization, while maintaining a low memory footprint and compatibility with AdamW. We also describe our model architecture, data distributions, token budget, optimizer implementations, and hyperparameter tuning strategies used in our experiments. Section: Initial verification of Muon's performance. In this section, we initially verified Muon's performance and quickly obtained positive results with our setup. We found that, regardless of the number of steps, Muon consistently achieved a lower training loss and reached the target loss faster than AdamW in terms of wall time. Next, we explored the compute time trade-off for pre-training. Traditional methods that compare optimizers based on wall time or efficiency do so using fixed resources, which doesn't capture the trade-off between resources and training time. Instead, we compared optimizers using ISO loss curves on a compute time graph, measuring the total training time to reach a target loss based on the number of devices and batch size. The difference between the curves indicates new, cost-effective options, such as shorter training times or fewer devices compared to other optimizers. We simulated how practitioners might use more devices to cut down training time by training models with 500 million parameters across 13 batch sizes, ranging from 128,000 to 16 million. While varying the number of devices from 8 to 128 to ensure sufficient memory. The resulting plots show that Muon expands the options available for resource allocation consistently across different thresholds and data distributions. The plots summarize Muon's efficiency compared to AdamW, considering all variables that influence the compute time trade-off. For example, increasing the batch size can raise the number of floating point operations per second, but it might also reduce the optimizer's data efficiency, requiring more operations to achieve the same loss. We also noted that our implementation of AdamW is standard and close to optimal, while our Muon implementation is basic, suggesting that further optimization could enhance its efficiency. Regarding Muon's relative data efficiency over AdamW, as we add more devices, we must increase the batch size to avoid memory issues. However, the data efficiency of an optimizer tends to decrease after a certain batch size, requiring more tokens to reach the same loss. We hypothesize that Muon remains more data efficient than AdamW at larger batch sizes. To measure this, we looked at the ratio of token consumption for both optimizers to reach a target loss. If this ratio stays above 1 and is increasing or stable at larger batch sizes, it indicates that Muon's efficiency does not diminish even with larger batches. Our observations with a 1 billion parameter model showed that the token ratio is above 1 and generally increases with higher losses, suggesting that Muon's advantages persist beyond fixed batch sizes. Interestingly, the extra tokens needed by models do not significantly depend on model size, as all tested sizes required about 2 billion additional tokens with AdamW compared to Muon to reach a target loss of 3.2 nets. This non-decreasing trend in token consumption indicates that Adam's overhead remains constant even at larger batch sizes, giving Muon an advantage in balancing compute resources and training time, despite Muon performing more operations than AdamW. Finally, we connected our findings to the concept of critical batch size, which is the largest batch size that allows for nearly perfect scaling. We defined the critical batch size as the point where the number of tokens needed to reach a loss remains constant for increasing batch sizes. Our empirical results showed that the token ratio is non-decreasing, providing insights into the behavior of both optimizers beyond the critical batch size. More detailed analysis can be found in the appendix. Section Summary. In this section, we demonstrate that Muon consistently outperforms AdamW in training efficiency, achieving lower training loss more quickly and expanding the compute time trade-off, which enhances resource allocation flexibility. Our analysis shows that Muon maintains superior data efficiency even at larger batch sizes, indicating its effectiveness in optimizing training time and resource use compared to AdamW. Section: Choosing hyperparameters for Muon. In this section, we discuss how to choose hyperparameters for Muon. We have highlighted the advantages of using Muon instead of AdamW during pre-training. To make the most of an optimizer, we need to efficiently select nearly optimal hyperparameters. We also raise the question of how well Muon works with standard hyperparameter transfer methods, like MUP. After outlining the sources of error in MUP, we present our first empirical demonstration of MUP for calibrating hyperparameters in a large language model using Muon. We recognize that conducting exhaustive grid searches over hyperparameters can be impractical for large models. For instance, if we have multiple hyperparameters each on a 6-point grid, we would need to train numerous models, which can be very costly. As an example, the largest model we trained had billions of parameters and took many hours to process a vast number of tokens. A simple grid search on this model would consume a significant amount of computational resources. Instead, hyperparameter transfer offers a more practical solution. We can train a smaller proxy model, fine-tune its hyperparameters, and then apply those settings to the larger model. However, we cannot assume that the best hyperparameters for the smaller model will work for the larger one without further analysis. MUP addresses this challenge by ensuring reliable hyperparameter transfer across different model sizes. We introduce the main ideas behind MUP and explain our choices for initialization, multipliers, and learning rate scaling. We define a parameterization of the network that depends on its width, using specific functions. Each weight matrix in a layer is adjusted based on trainable parameters, which we initialize in a certain way, and we set the learning rate based on a base rate. Next, we analyze the main sources of error in hyperparameter transfer using MUP. We will later present a simple algorithm to manage and reduce these errors. Our analysis relies on the understanding that neural networks can often be approximated in the limit of infinite width. We assume that this limit exists and is smooth as we increase the width of the network. By using a straightforward reparameterization, we can apply a Taylor expansion to understand the implications of using finite widths for hyperparameter transfer. From our analysis, we see that using any finite width introduces some imprecision. The theory we discuss allows for principled hyperparameter transfer from smaller to larger models by aligning their training dynamics. However, recent experiments show that this transfer is only approximately valid, with errors decreasing as the model width increases. This observation supports the idea that hyperparameter transfer becomes exact only in the infinite width limit. We identify two main sources of error in the MUP transfer process. First, the optimal hyperparameter for a given loss function at a finite width differs from that of its infinite width counterpart due to corrections. This finite width bias is an unavoidable error unless the proxy model is sufficiently large. Second, when we estimate the optimal hyperparameters using a grid search, we can introduce sampling errors, especially if the grid is coarse or poorly chosen. In the next section, we will introduce an algorithm to address both sources of error effectively. Section Summary. In this section, we discuss the importance of efficiently calibrating hyperparameters for the Muon optimizer, highlighting the challenges of traditional grid searches for large models and introducing the maximal update parameterization, MUP, as a solution for effective hyperparameter transfer across model scales. We also identify two primary sources of error in this transfer process, emphasizing the need for a new algorithm to mitigate these issues. Section: The Telescoping Protocol. In this section, we present the telescoping protocol, which offers a practical way to manage errors systematically. Our telescoping algorithm is based on the idea that, due to the identified sources of error, we can train models at various widths while also reducing the number of grid points at larger widths to save on costs. The concept of efficiently managing resources for hyperparameter searches is not new, and our approach of logarithmically narrowing the search space aligns with hierarchical Bayesian optimization. Our analysis shows that the compute budget for final model training can vary significantly, depending on the desired confidence level, but typically saves more than a brute force grid search. This leads to substantial savings in large-scale training. The key assumption of our telescoping method is that the best hyperparameter changes smoothly with model width. When we double the width, which increases the computational load, we can have the mesh spacing to keep track of this change while maintaining a proportional number of samples for each hyperparameter at each stage. This keeps the cost of each stage roughly constant, preventing both under-refinement and over-refinement. We start with a broad initial sweep at the smallest width, using prior knowledge about feasible hyperparameter ranges. As we double the width, we narrow the mesh just enough to capture any small shifts in the optimum. If no new peaks appear at larger widths, this half-meshing strategy is nearly optimal, balancing accuracy and finding the best hyperparameter with computational efficiency. Each refinement stage has a similar cost, so for a final model compute cost, this method only adds a small factor to the computational needs for hyperparameter tuning, ensuring that the final training run still uses a significant portion of the overall budget while keeping tuning overhead modest. We validate our telescoping algorithm on a set of transformer models targeting around 94 billion parameters. All models use a sequence length of 150, a batch size of 151 million tokens, and a depth of 152 layers. The smallest model has specific dimensions for heads and embeddings, and we do not scale the AdamW parameter since our models are small enough. We fix all other dimensions and only vary the width. For the largest model, we train for a specific number of steps, which corresponds to a substantial number of tokens, slightly exceeding the optimal budget. However, overtraining can be advantageous for achieving a smaller inference footprint. The complete hyperparameter sets are derived from various dimensions, and we maintain a fixed head dimension across experiments. We train on a mix of high-quality web data and Python code. We apply our telescoping algorithm to refine hyperparameter sweeps while doubling the model width, geometrically reducing the search space. The performance variation at the largest scales is not statistically significant, suggesting that we could have stopped the remeshing earlier without losing accuracy. Our results indicate that each iteration of the telescoping process reduces variance, supporting both precision and accuracy. The final training of the 94 billion parameter models achieves a low training loss, outperforming previous models at smaller widths. We find strong agreement with a shifted power law, with the exponent for parameter dependence being close to the chinchilla exponent. Section Summary. In this section, we present our telescoping algorithm, which efficiently manages hyperparameter tuning by systematically reducing the search space while training models at varying widths, ultimately balancing accuracy and computational efficiency. Our experiments on transformer models demonstrate that this approach significantly reduces computational costs while maintaining high performance, achieving a final training loss that surpasses previous models. Section: Dethroning AdamW. In this section, we discuss the limitations of AdamW, which has been the leading optimizer for training large neural networks. While recent studies have explored new optimizers, particularly second-order methods with non-diagonal preconditioners, they often compare these optimizers under fixed computing resources without clearly demonstrating that any of them outperform AdamW in balancing compute and time. We aim to fill this gap by showing that Muon enhances the compute time Pareto frontier established by previous research. We also examine the impact of batch size on training. Most studies focus on a critical batch size, which is the largest size that allows for nearly linear scaling, beyond which we see diminishing returns. While this estimate is helpful, it is sensitive to noise and does not adequately capture the effects of batch size in the post-critical phase, which is important for compute time trade-offs. We introduce a new method to continuously assess the batch size advantage of an optimizer in this post-critical phase by tracking the ratio of token consumption. Regarding MUP, we note that while many studies have explored this concept, our work stands out in several ways. MUP has been shown to be theoretically sound, linking infinite width limits to the behavior of finite width networks. Although previous research has demonstrated its empirical effectiveness, they often lacked thorough investigations of the errors we address. Our study not only critiques a specific assumption in MUP's derivation but also includes extensive experiments that showcase MUP's practical behavior. We also discuss various scaling parametrizations and highlight a new technique called meta-P, which stresses the importance of accurately transferring hyperparameters across different scales, such as depth, batch size, sequence length, and training steps. However, these transfers are only approximately valid. Additionally, while there have been proposals to apply MUP to second-order optimization methods like shampoo and KFAC, empirical validation of MUP alongside Muon is still lacking. Notably, we have demonstrated that the MUP scaling used for AdamW is also applicable to Muon, reinforcing the compatibility of Muon's hyperparameter transfer properties with those of MUP, as supported by existing literature.